It's crazy, isn't it? How much of the technology we take for granted, the stuff we use every day, it all comes back to a programming language that's been around, well, I guess for over 50 years now.
Yeah, you're talking about C, right?
Exactly. C. It's like when you really dig into our devices, peel back the layers of all the apps and software, so often you hit this kind of bedrock, this like foundational layer.
Yeah.
C. It's the core of operating systems like UNIX. And it's running, countless embedded systems, little tiny computers, basically everywhere from your car to, complex industrial machines.
It's kind of amazing, yeah. You've got this whole world of, like you said, apps and languages and frameworks popping up all the time, and yet C just keeps going strong.
Right. So for this deep dive, we're going deep, deep into C. And we're taking a really interesting approach. We're basically using the original blueprint.
Blueprint.
Well, yeah, like we're going to explore the fundamental ideas of C by looking at the C programming language,
Yeah.
second edition, by Brian Kernighan and Dennis Ritchie.
Ah, the K&R book. Classic.
Right. And the second edition, it's especially important because it lines up with the NSIC standard, right? It was a big deal. It really solidified C's place, I guess.
It's true. Standardization, that's a turning point for any language that wants to become, well, ubiquitous.
Okay, so maybe quick introductions are in order here. For anyone who's not immediately jumping up and down at those names, Kernighan and Ritchie, there's C they created.
At Bell Labs, yeah. Back in the early 70s. And they weren't just language designers either. They were key in the development of UNIX. It's hard to overstate their impact, honestly.
Seriously. They shaped how we think about like computing on a really deep level. So this deep dive, it's like we're going back to the source. We're going to try and understand C through the eyes of, well, its creators.
It's a direct line, yeah, to the thinking, the choices, the philosophy behind the language.
Exactly. So the mission here, if you choose to accept it, I guess you already have since you're listening, is to get this shortcut, I guess, to understanding the essence of C, why it was so important and why it still matters so much today.
The core principles, the foundational ideas that have stood the test of time, and that, well, continue to influence even the most modern programming landscapes.
So where do we even start with a story like this? Like, how did C come to be in the first place?
Okay, so the story of C, it actually starts at Bell Labs back in 1972. And the original purpose, the first big goal, was pretty specific. They needed a language to write the UNIX operating system.
Ah, so it wasn't like this grand plan for, a general purpose language to rule them all.
Well, not initially, no. But, its utility, how adaptable and useful it was, that became pretty apparent quickly. So to understand C, you kind of have to understand its lineage, its history. It evolved from another language, BCPL, and was also influenced by, well, a language just called B. These were, more rudimentary languages, but C, it built on their concepts. Importantly, it added things like a more sophisticated type system.
Okay. So it was very much engineered for these like low-level system tasks from the get-go.
Yeah, very much so. It's usually classified as, you'll see this everywhere, a system programming language. And the reason is it was meant to give programmers this kind of fine-grained control over the hardware, the computer's memory and all that, perfect for writing things like operating systems and compilers, the tools that, make other software possible. But what's really remarkable about C is that it wasn't just limited to those core system tasks. The efficiency and flexibility you get with C, it turns out it makes C surprisingly well-suited for a much, much wider range of problems.
That's interesting. So you mentioned efficiency and low-level control. What does that even mean in practical terms, though? Like, if you're not a programmer who's used to, working with C, what's the big deal?
Okay, so one of the things that's really unique about C is that it gives you a lot of direct control over things like how memory is used, how the resources of the computer are allocated, much more so than most modern languages. It's powerful, but it also requires a lot of care and understanding of how the underlying systems actually work. And here's the cool part. It manages to do this while still being incredibly portable. A well-written C program can often be compiled and run on totally different types of computers with very few modifications.
So it's like you get this close-to-the-metal performance, but you're not, like, locked into any particular hardware. Right?
Precisely. And the language itself, it's pretty concise. It's often called low-level in the sense that its concepts are very close to the actual architecture of a computer. And this is a big part of why it's so fast, so efficient.
You also mentioned the ANSI standard before. Why was that such a defining moment for C?
All right, so think about it this way. In the early days of C, You had all these different compilers popping up, which is great. But the problem was they all had these subtle little variations in how they implemented the language, inconsistent implementations. The ANSI standard, which was established in 1983, it was a way to bring order to the chaos. It provided a clear and, more importantly, a machine-independent definition of what C actually is. It was like setting down the official rules of the game.
And the K&R book that we're using for this deep dive, that came out right as this standard was solidifying, right?
Yeah, exactly. It was perfectly timed. It reflected this standardization, which was essential. It meant that C programs could be, reliably moved and run on different systems without weird compatibility issues. And it meant that programmers could all be on the same page about, what C code was supposed to do.
Okay, so it was about bringing consistency
Yeah.
and, fostering this kind of wider adoption of the language.
Right.
Makes a lot of sense. So let's get into the real nitty-gritty here. What are the absolute fundamental building blocks of C? If you're sitting down to write a program, where do you even begin?
At the most basic level, a C program, it usually revolves around what's called the main function. This is where everything starts, the entry point of your program. And, a really common first step you'll see is including the standard input-output library. This is done with, you'll see this all over, #include cdo.h. What this does is it brings in functions that allow you to interact with the system. Things like reading input from the user or printing output to the screen.
Right, makes sense. So you've got this main function, and then inside that function, you're going to need to start working with, data.
Yeah.
Data, the heart of it all. So in C, you use what are called variables to hold that data. A variable is basically a named location in the computer's memory. Think of it like a container where you can store a piece of information. And each variable, it has a specific type that tells the compiler, what kind of data it can hold, numbers, characters, and so on. So going back to, if you were writing a program to convert Fahrenheit to Celsius, which is a classic C example, you might start by declaring integer variables to store the Fahrenheit temperature, the Celsius temperature, maybe a variable for the step size you want to use in the conversion, things like that.
So variables, it's all about giving names
Yeah.
to these little chunks of memory. How do you actually set them up in C? To declare a variable, you tell the compiler its type, and then you give it a name. So you might write something like int var Celsius. This tells the compiler, hey, I need 2 integer variables, one named var, one named Celsius. Set aside some space in memory for them. You can also assign an initial value to a variable when you declare it. So you could write something like int lower equals 0. This creates an integer variable called lower and sets its initial value to 0.
Right. And you said int is for whole numbers, right? Integers.
Yeah.
What other basic data types are there in C?
Oh, yeah, there are a few. You've got char, which is for storing single characters. Think of it as a single byte of memory. Then there are integer types that come in different sizes. You've got short, int, and long. And these typically represent signed integers, meaning they can be positive or negative. And then for numbers with decimal points, you've got float for single precision floating point numbers. And then you've got double for double precision, which gives you, more precision. It's like more decimal places, essentially.
So you've got all these different containers for different kinds of data. How do you actually do stuff with them? Like, how do you do math, or how do you compare values?
Okay, that's where operators come in. C has all the standard arithmetic operators you'd expect, plus for addition, for subtraction, for multiplication, for division, and then you've got percent, the modulo operator, which gives you the remainder of a division.
Ah, yes, modulo. Classic.
Now, one really important thing to keep in mind with division in C, it's something that trips people up all the time, is that if you're dividing 2 integers, the result will also be an integer. Any fractional part, it just gets chopped off. Truncated, as they say.
Ah, okay. Yeah, I've definitely seen that causing a head scratching in my early programming days.
Yeah.
So if you're doing like that Fahrenheit to Celsius conversion you mentioned before, how would you express that in C, keeping this whole integer division thing in mind?
Right. So a naive way to write it would be something like Celsius equals 5, var here 32, 9. But if var 32 happens to be an integer, this whole thing's going to be an integer division. So if you want to get a floating point result, with those decimal places, you typically make sure there's a floating point number in that calculation. You could do something like Celsius 5.0, 9.0, or 32, or cast one of those integers to a float.
Ah, so you can force it to use floating point math. Good to know. Now, how do you actually get results or messages or anything to show up on the screen?
That's where the print function comes in. Like I was saying earlier, you need to hashtag include studio.h at the top of your program to use it. It's really powerful. You give print what's called a format string, and it's enclosed in double quotes. Think of it like a template. It tells print how to interpret and display any additional arguments you give it. Like you might have um, print amp var Celsius. This would print the integer value of the var variable, then a tab character, then the value of Celsius, and then finally a new line character. So it moves the cursor to the next line. And those precedate things, those are format specifiers that say, hey, put an integer here.
Okay, so that's how you control the layout and the way the data is presented. You also mentioned something called symbolic constants earlier. Can you elaborate on those?
Oh, yeah. Symbolic constants. They're great. They're created using the hashtag define preprocessor directive. For instance, hashtag define lower zero. This tells the preprocessor, which is like the part of the compiler that runs before the actual compilation, to replace every instance of lower in your code with the value 0. What this means is it's not like a variable where, the value could change while the program is running. It's like a straight up textual substitution.
Okay. But why use symbolic constants? It seems like you could just type, 0 directly wherever you need it.
Well, yeah, you could, but think about it this way. Let's say you've got, the lower limit of a temperature range in your program, and you're using that value in like several different places. If you hard code the number 0 everywhere, and then you decide, oh, actually, the lower limit should be 10 now, you have to go hunt down all those instances of 0 and change them.
And that could get messy real fast.
Exactly. Symbolic constants make your code much more readable and easier to maintain. You just change the hashtag define at the top, and the change ripples through your entire code. And using, a descriptive name like lower instead of just a number makes it a lot clearer what that value represents in the context of your program.
So it's about organization and readability, especially as your programs get more complex.
Mm-hmm.
Now, what about getting input into a C program? Like, if you want the user to type something in.
Right. So at the most basic level, for character-by-character input and output, C has these functions called getchar and putchar.getchar. It just reads a single character from the standard input, which is usually the keyboard, and it returns the integer representation of that character. And then putchar, it takes an integer that's treated as a character, and it writes it to the standard output, which is usually the screen.
And how are individual characters like letters or symbols, how are they represented inside a C program?
Okay, so character constants in C, they're enclosed in single quotes, like A. But under the hood, what's actually happening is they're stored as numerical values. These values correspond to, to a character encoding standard like ASCII, which stands for American Standard Code for Information Interchange.
Oh, yeah, ASCII. That brings back memories of those early computing classes.
Right. So, for instance, the ASCII value of the character A is 65, and C also has these special escape sequences, which are really helpful. They start with a backslash, like N, to represent a new line character, which moves you to the next line, or T for a horizontal tab.
Yeah, escape sequences. They're essential for formatting output and handling those characters that you can't easily type directly. Now, how about when you're working with, whole words or sentences, sequences of characters?
Right. So those are called string literals in C. And they're enclosed in double quotes like, hello world. And it's really, really important to understand that in C, a string literal, it's actually treated as an array of characters. And what the compiler does is it automatically adds this null character 0 at the end of the string. It's invisible when you type it, but it's there in the computer's memory. And this null character, it acts as a sentinel. It's like a signal telling functions that are working with strings, hey, this is the end of the string, stop here.
So even though you don't see it when you write the code, that null terminator is there working behind the scenes. That makes a lot of sense. So we've got all the arithmetic operators for doing math. What other kinds of operators does C have for, manipulating and comparing data?
Oh, C has a whole arsenal of operators. You've got relational operators, which means equal to, and then you've got thens, not equal to, and then the greater than and less than symbols, S, and then greater than or equal to and less than or equal to.
Right, those are essential for, for making comparisons, for figuring out how two values relate to each other.
Exactly. And these operators, they evaluate to either true, which is represented as 1 in C, or false, which is represented as 0. And then you've got logical operators. These are like the building blocks for Boolean logic. So you've got N, that's logical A and D. You've got len, which is logical OR. And then you've got the exclamation mark, len, for logical not. So, for example, you can use the A and D operator, NN, to check if two conditions are both true.
It's amazing to think that, like, all these complex logical decisions and operations, it all comes down to these simple symbols. But what happens when you're working with different types of data in the same operation? Does it handle that gracefully?
That's a great question. And it brings us to the topic of type conversions. C allows for both implicit and explicit type conversions. So an implicit conversion happens automatically. Like if you're doing math and you have an integer and a floating point number in the same operation, the integer usually gets promoted to a floating point type before the operation's actually done. This ensures you get a floating point result. And then you've got explicit conversions. You can specifically tell C to convert a value from one type to another. You do this using a cast. It's like float integer variable. This explicitly converts the value of integer variable into a floating point number. The problem is you have to be careful because sometimes when you do these explicit conversions, you can lose information.
Yes.
A classic example is if you convert a float to an int. You know, floats have those decimal places, integers don't. So when you do that conversion, the decimal part, it just gets truncated. It disappears.
Okay, so it's like trying to fit a round peg into a square hole. You might lose a little bit of the peg in the process. Speaking of little symbols, you often see these plus plus and operators in C. What are those all about?
Right. Those are the increment and decrement operators. So plus plus is increment and is decrement. They're really just shortcuts. They let you increase or decrease the value of a variable by 1.
Okay, so why not just use +1 or 1? Is it just about saving keystrokes?
Well, partly yes, it does make the code more concise, but there's a subtle difference that can be really important. You can use these operators in two ways, prefix and postfix. So prefix would be like plus I, where you put the operator before the variable. Postfix is I plus I, the operator comes after.
And what's the difference?
The order of operations. With prefix, you increment or decrement the variable before its value is used. With postfix, you use the value and then you increment or decrement.
So prefix, change, then use, postfix.use, and change.
Got it. Okay, now C's always been known for its low-level programming capabilities. Does it have special operators that reflect that kind of close-to-the-metal approach?
You bet it does. C has these things called bitwise operators,
Yeah.
and these are for working directly on the individual bits that make up the data in memory, like the zeros and ones.
Right, the really fundamental stuff.
Exactly. So you've got and for bitwise AND, for bitwise OR, for bitwise XOR, that's exclusive OR, and then you've got and for left and right bit shifting. And then there's the bitwise not. These are super powerful, but, they can be a bit tricky to wrap your head around if you haven't worked with them before.
I can imagine. What kind of situations would you even use bitwise operators for? All sorts. If you're working with hardware registers, setting and clearing flags, or just doing anything where you need very fine-grained control over how the data is represented in binary form, bitwise operators are your friends. For example, you might use a bitwise AND to check if a particular bit in a status register is set, that kind of thing.
So it's really about getting down to the most fundamental level of how the computer stores and processes information. Pretty cool. Now, we saw how to use the assign to assign initial values to variables. Are there other ways to assign values in C?
Yeah, the equal sign is the basic assignment operator, but C also has these compound assignment operators, which are kind of neat. They let you combine an arithmetic operation with the assignment. So, for example, x plus y is a shorthand way of writing x plus y. It just saves you a bit of typing. And you've got, similar ones for subtraction, multiplication, division, and modulo.
Okay, so it's about making the code a little more concise. What about, those situations where you want to assign a value based on a condition? Like, if this is true, assign this value, otherwise assign that value.
Right. So C has this really handy thing called the conditional expression, which is sometimes called the ternary operator. It looks like this. Condition.expression1.expression2. What it means is if the condition is true, the result is expression 1. Otherwise, it's expression 2.
So it's like a one-liner for simple if-else assignments.
Exactly.
Okay. So we've got all these operators flying around. How does C decide what order to evaluate them in when you have a more complicated expression?
Okay, that's a great question. It's all based on what's called operator precedence and associativity. Precedence is just, it sets a hierarchy. telling you which operations are done before others. Like multiplication and division have higher precedence than addition and subtraction, just like in regular math. And then associativity comes into play when you've got multiple operators with the same precedence. It determines whether things are evaluated from left to right or right to left.
So it's like the order of operations that we all learned in school but applied to programming.
Yeah, pretty much. But to avoid any ambiguity, to make sure that that your expressions are evaluated exactly how you want them to be, it's always best to use parentheses liberally. Parentheses let you explicitly group operations and control the order in which things happen.
So parentheses, they're like the ultimate way to enforce order in your code.
Right.
Okay, so now that we have variables to store data and operators to manipulate it, how do we make our programs, do different things based on different conditions? How do we get them to make decisions?
That's where control flow structures come in. So the most basic one is the if statement. It lets you say, hey, if this condition is true, execute this block of code. And then you can have an optional else clause. If the if condition is false, the code in the else block gets executed. And you can even nest these if-else statements, like you can have an if statement inside another if statement and so on to create more complex decision trees.
Right, so you can create these branching paths for the program to follow.
Yeah.
And you mentioned block structure earlier. Does that relate to these if statements and things like that?
Yeah, absolutely. So a block of code in C, it's just a group of one or more statements enclosed in curly braces that root them. And you can declare variables inside those blocks. So if you declare a variable inside an if block, it only exists, it only has scope within that block. Once the program moves on, that variable is gone, like it never existed.
So it's like creating these little isolated environments within your program.
Exactly.
Okay, what about those situations where you have multiple different conditions that you need to check, but they're all like mutually exclusive? Only one of them can be true at a time.
Oh, yeah. For those situations, C has a few options. One is the else-if construct. It lets you chain together a series of conditions. So the program checks the first condition, and if it's true, it executes the corresponding block of code. If not, it moves on to the next else-if, and so on. And then there's the switch statement. It's really handy for those situations where you're checking against a set of specific integer values.
Okay, so you'd use a switch statement when the decision making is based on like a limited number of possible whole number values, right?
Yeah, that's a good way to think about it. You provide different case labels for each possible value, and the program executes the code for the matching case. And it's super important to include a break statement at the end of each case block unless you specifically want the program to fall through to the next case. That can be a common source of bugs if you're not careful.
So if else for more general conditions. And switch when you've got these well-defined integer values to work with.
Got it. Now, how do we make our programs do things repeatedly, without having to write the same code over and over again?
That's where loops come in. So one of the simplest is the while loop. It just keeps executing a block of code over and over again as long as a certain condition is true.
So it checks the condition, and if it's true, it runs the con, checks again, runs again, and keeps going until the condition is false.
Exactly.
Yeah.
And then you have the for loop. This one is, it's a bit more specialized. It's usually used when you know exactly how many times you want to repeat something. You set an initial value, a condition that's checked each time through the loop, and then an increment or update expression that's run at the end of each loop iteration. It's really common for iterating over, a fixed number of items in an array or something like that. So with for loops, you're usually working with a counter that gets incremented each time.
Often, yes. But you can get really creative with what you do in that update expression. It doesn't have to be a simple increment. And it's important to note that in many cases, you can actually rewrite a for loop as a while loop, and vice versa. They're equivalent in terms of what they can accomplish.
So they're both tools for repetition.
Exactly. And then finally, you have the do while loop. It's very similar to a while loop, except that the condition is checked at the end of the loop rather than the beginning. What this means is the code inside a do while loop, it's always going to execute at least once.
Right. That's a key distinction. What happens if you need to, jump out of a loop early before the condition is false, or maybe skip the rest of the current iteration and move on to the next one?
Good question. C gives you two special keywords for that, break and continue. Break completely terminates the loop right then and there, and the program continues from the line after the loop. Continue, on the other hand, it skips the rest of the current loop iteration and jumps back to the beginning of the loop to check the condition again.
Okay, break to exit, continue to skip. Got it.
Yeah.
In some older programming languages, you see this thing called the go-to statement. Is that a thing in C?
Oh boy, go to. It's definitely a thing, but it's generally something to be avoided if at all possible. Go to lets you jump to a specific labeled point in your code. It can create these really convoluted paths of execution, making your code super hard to read and understand.
So it's best to steer clear of go-to for the sake of everyone's sanity, including your own, right?
Pretty much. There might be some very, very rare cases where GoTo could be useful, like in some very specific low-level programming situations, but in general, it's best to stick to those structured control flow mechanisms. If,
Hmm.
else, switch, while, and for, they help to keep your code much cleaner, more organized, and much easier to debug.
Okay. Go-to. Avoid if at all possible. Noted. Now, as our programs get bigger, more complex, we need ways to break them down into more manageable chunks. How does C help with that?
Right. That's where functions come in. A function is essentially a self-contained block of code that does a specific task. They're like mini programs within your larger program. And they're absolutely crucial for making large programs more understandable, easier to work with, and reusable. To define a function in C, you give it a name, you specify what type of value it returns, and you define the inputs or parameters that it takes, and then the actual code that the function executes, that's all enclosed in curly braces.
So a function is like a specialized worker that performs a specific task when you call its name. And it can receive instructions in the form of parameters, and it can send back a result, right?
Yes. And before you can actually use a function, the compiler has to know about it.
Mm.
So you usually either define the function completely or you declare its prototype. The prototype just tells the compiler the function's name, its return type, and the types of its parameters. It's like a declaration of intent, basically.
So the prototype is like the function signature,
Yeah.
telling the compiler, hey, this function exists, and this is how you use it.
Exactly. You'll often see function prototypes in header files, which are those .h files that you include at the top of your program. And the actual function definitions, they're typically in the .c files.
So it's about separating the what it does from the how it does it. Makes sense. Now, how do you actually send information into a function when you call it, and how do you get results back from the